Welcome to section 1.5 Permutations and Inverses, lecture 7. This is Dr. Gilbert, Eyabi. We are using the text Elements of Modern Algebra 8th edition by Gilbert and Gilbert. Subsection 1.5.1 Permutation. A one-to-one correspondence from a set A to itself is called a permutation on A. So if F is a mapping from A to A and F is injective or one-to-one, we say that F is a permutation on A. Now, for any non-empty set A, we would adopt the notation SA to mean the set of all permutations on A. And the set of all mappings would be denoted by MA. So let me break that down for us a little bit. So whenever we see SA, it means the set of all permutations on A. Now to put this in the set notation, this will be the set of all mappings F from A to A such that F is a permutation. In other words, the set of all mappings F from A to A such that F is one-to-one. So if an element F is in SA, remember elements in SA are mappings, not X or Y, mappings. So F is in SA if and only if F is one-to-one. And do not forget, F is a mapping from A to A. Now, in general, we would use the notation MA to mean the set of all mappings from A to A. So an element F is in MA if and only if F is a mapping from A to A, not necessarily one-to-one. In other words, we can quickly see that the set of all permutations is a subset of MA. So as we move on, I will say a lot about elements of MA and at times element of SA. I expect you to know what it means for a function to be in MA and what it means for a function or a mapping to be in SA. Now let me proceed by defining the identity mapping. Just like we have the identity element in the set of real numbers, in the set of integers, and so on and so forth, or in a non-empty set A, we define the identity element E as that element such that for any arbitrary element X in the set A, X star E equals E star X equals X. That is the identity element. MA is a set. The only difference here is that instead of having elements like X, Y, Z, our elements in MA are actually mappings. And yes, we can talk about the identity element in MA. So we define the identity map IA in MA as follows. It is the map such that IA of X equals X for every X in A. So the identity map maps every element to itself. So any map you find in MA that maps an element to itself would be the identity map. Now let's discuss a little bit the concept of MA with respect to the concept of binary operations, which we saw in lecture 6, section 1.4. Firstly, I want you to observe that MA under star, where star is our composition notation, is actually a binary operation. If I take any two functions, F and G in MA, and I compose them, I get a function from A to A. That is a mapping in MA. So this binary operation is well defined. Our star is composition. So let's define this a little more rigorously. Define the binary operation star on MA. Again, don't forget MA is the set of all functions F from A to A. So define star on MA by F star G equals F composed with G for every FG in MA. Why don't we investigate some of the things we are used to when talking about binary operations? Number one, MA under the operation composition is not commutative. If you go back to sections 1.2 and 1.3, you realize that F composed with G is not necessarily the same as G composed with F, even if both F and G are mappings from A to A. So we can say that MA under the operation composition is not commutative. You can go back and check the lectures from those sections. Number two, what about associativity? Yes, go back to sections 1.2 and 1.3. We did prove that F composed with G composed with H was the same as F composed with G composed with H. So MA under the operation composition is associative. Identity element. For every F in MA, by the definition of our binary operation star, F star IA is simply F composed with IA. Now, let us verify that MA under composition actually has an identity element, and that identity element is nothing but our IA, which we defined previously. So F star IA of X is the same as F composed with IA by the definition of our binary operation star. And this is the same as F of IAX by the definition of composition. But what is IAX? Since IA is the identity map, this is simply equal to F of X. That is by the definition of IA. Now, since this holds for every X in A, remember, two functions are equal if and only if they agree at every point in their domain. Since this holds for every X in IA, we can conclude that F composed with IA, which is F star IA, equals F. We now just have to verify that IA star F equals F. Then we would conclude that IA is actually the identity in MA. Now let's look at IA star F. IA star F of X equals IA composed with F of X for every X in A because of the definition of our binary operation star. Now, by the definition of composition, this is the same as IA F of X. But remember that IA is a mapping from A to A, and F of X is an element in A. So what does IA do when IA comes in contact with any element from A? It simply gives back that same element. So IA of F of X simply equals F of X. But this holds for every X in A. What does that mean? IA star F equals F. So we have just shown that F star IA equals F and IA star F equals F, and therefore we can conclude from 1 and 2 that IA is the identity in MA under the operation composition. Now, what about left and right inverses? Of course, if an element in MA has left and right inverses and both are equal, then that would be the inverse of that element in MA. Is there a general statement like every element in MA would have to have an inverse? Let's define F and G in MA as follows. F of n equals 2n, and G of n equals n over 2 if n is even, and 4 if n is odd. We can quickly verify that G is a left inverse of F. In other words, G composed with F of n is exactly n, and that is IA. But if we compose G to the right, we would discover that F composed with G is different from IA. So G is the left inverse of F, but G is not a right inverse of F. In other words, F does not have an inverse. It has a left inverse, but does not have a right inverse. And by the way, for this example, our non-empty set A is the set of integers. The next question, can you find mappings F and G such that F composed with G equals IA and G composed with F equals IA? If that happens, then G would be the inverse of F, or F would be the inverse of G. Now, this is where you come in. I want you to define two maps F and G in MA, where A is the set of integers, such that F composed with G is IA and G composed with F is IA. In that case, F would be the inverse of G and G would be the inverse of F. Let me give you one quick example. Define F and G in MZ, where your A is Z, the set of integers, by F of n equals n plus 1 and G of n equals n minus 1. Verify that F is the inverse of G and G is the inverse of F, and generate your own example, something a little bit more sophisticated than n plus 1 and n minus 1. I leave that as a simple exercise for serious students. Subsection 1.5.2 lemma, left inverses and the one-to-one property. If A is a non-empty set and F is a mapping from A to A, that means F is an element of MA, then we say that F is one-to-one if and only if F has a left inverse. We could consider this as a test for the existence of left inverse. If I give you a function and I ask you, does this function have a left inverse? All you do is you quickly check if the function is one-to-one. If it is, then a left inverse exists. And on the other hand, if a left inverse exists, then it is one-to-one. Let's go ahead and prove this little lemma. We're going to prove the reverse direction first. Suppose F from A to A has a left inverse G. Okay, what that simply means is that G composed with F is the identity map, IA. We want to show that F is one-to-one. So assume F of x1 equals F of x2, where x1 and x2 are elements in A. We have to verify that x1 equals x2. But F of x1 equals F of x2 implies that G of F of x1 equals G of F of x2. By definition of composition, G composed with F of x1 equals G composed with F of x2. But what is G composed with F? IA. And what is IA of x1? X1. So G composed with F of x1 is simply x1, and G composed with F of x2 is simply x2. And that is because G composed with F equals IA, and we know the definition of IA. So we assume that F of x1 equals F of x2, and we have verified that x1 equals x2, and therefore we conclude that F is one-to-one. The forward direction. Suppose F is one-to-one. We want to find a mapping G in MA such that G composed with F equals IA. This is done by construction, and I would leave the details as a simple exercise for serious students. And for the students taking this with me right now, I would expect you to show me the details of the forward direction in class. 1.5.3 lemma, right inverses and the onto property. If A is a non-empty set and F is an element of MA, then F is onto if and only if F has a right inverse. So, just like the previous lemma, this is a characterization for right inverses. If I give you a function and I ask you to determine if a right inverse exists, all you have to do is verify that the function is onto. If it is, then it has a right inverse. Proof. The proof of this lemma for the forward direction, you would suppose that f is onto and then construct a function g that is a right inverse of f. And for the reverse direction, you would suppose that f has a right inverse g and then verify that f would have to be onto. The details of this proof would be left as a simple exercise for serious students. I want us to summarize what we have so far. Number one, f from A to A is onto if and only if f has a right inverse. F from A to A is 1 to 1 if and only if f has a left inverse. We did see back in sections 1.2 and 1.3 that f from A to B does not have to be equal to A, is invertible if and only if f is both 1 to 1 and onto. That is interesting. So if f is both 1 to 1 and onto, then f inverse exists. What if this b is actually equal to A? Do I need f to be both 1 to 1 and onto for f to have an inverse? Define the mapping f from z to z. Our non-empty set A here is a set of integers. We already verified that f is not onto, but f is clearly 1 to 1. So this function only has a left inverse, but not a right inverse. Example 2. Define the function h from z to z. Again, our non-empty set A here is a set of integers z by h of x equals x minus 2 on 2 if x is even, x minus 3 divided by 2 if x is odd. Then verify this, of course, that h is onto, but h is not 1 to 1. In other words, h has only a right inverse. So in what scenarios can we find a function that is both a left inverse and a right inverse so we can call it the inverse? Question. Find a map f that is both 1 to 1 and onto, and f is a mapping from A to A. Then we can conclude that a left inverse exists and a right inverse exists and would both be equal to imply that f is actually invertible. Think about these things as a serious student. But I am not going to leave you without stating the main theorem in this section. 1.5.4 Theorem, Inverses and Permutations. If f is a mapping from A to A, then believe it or not, f is invertible if and only if f is a permutation on A. It's actually easy. Use the two lemmas above and the fact that if f is invertible, then f is 1 to 1 and onto. Now, don't forget that a permutation is a 1 to 1 correspondence from A to itself. And I would leave the details as a simple exercise for serious students. But what I want you to remark is that if f is an element in MA, A not empty, then f is invertible if and only if f is a permutation on A. Now let's look at some problems for you to enjoy at your personal time. Problem number 1. Prove that if f is a mapping from A to A and f is a permutation, then f inverse is also a mapping from A to A and it is also a permutation. F permutation implies f inverse is a permutation. Question number 2. Let f and g be permutations on A. I want you to prove that f composed with g inverse equals g inverse composed with f inverse. Hint on this one. Do not forget that F inverse equals G if and only if G composed with F equals IA equals F composed with G. Once more, for those taking the class with me, we would prove each of these in class. Thank you, God bless you, and see you in lecture 8.